Hello everyone, my name is Pranab Kundu. Today I am going to discuss about the basics of symmetry and group theory. Now, this is a very interesting and conceptual topic and is very useful from the perspective of CSIR-NET, NET, GATE and JAM exam. Now, what type of question asked from this chapter? Generally, questions asked from this chapter either from point group of a molecule or from the character table of a point group. Now, before going to the point group determination of a molecule, we have to understand what is the symmetry of a molecule. Now, if you look at a butterfly, you see its one half will be the exactly mirror image to the other half. So it consists of symmetry. Now, scientifically, symmetry is the number of symmetry elements. Now, what is symmetry elements? Symmetry element is a geometrical entity which may be either a point, plane or a line with respect to which one or more symmetry operation can be takes place. So it may be a point, it may be a line or it may be a plane with respect to which one or more symmetry operation can be takes place. Now, so a new term arises which is the symmetry operation. Now, before going to the symmetry operation, we have to understand what is equivalent configuration and what is identical configuration. Now, equivalent configuration and identical configuration. Okay. For that, let's take an example of water molecule. We all know what is a bend structure and the angle HOH angle is about 104 degree. So if we pass an imaginary line through this oxygen atom and rotate the molecule is about 180 degree clockwise direction, we get, and if we label these two hydrogen as a H1 and H2, then after rotation it will get H2 H1 and the position of H1 and H2 are interchanged. These two are called equivalent configuration. Okay, and if we further rotate this molecule, this H2 molecule by 180 degree angle clockwise, we get H2 molecule where the position of H1 and H2 are same to that of initial configuration. So these two are the identical configuration. Clear? Now what is symmetry operation? Symmetry operation is an operation which may be a rotation, reflection or inversion with respect to rotation line line, this is the plane, and this is about the point. We get equivalent configuration. Clear? Okay. So symmetry operation is an operation which may be a rotation, reflection or inversion with respect to line, plane or point, so that we can get an equivalent configuration to the original on. Okay. Now let's tabulate various types of symmetry operation and corresponding symmetry elements as is the symmetry operation, symmetry elements, and it is denoted by denotation. Now first symmetry operation is rotation, and the corresponding symmetry elements is called axis of symmetry. Clear? And it is denoted by Cn. Now the second one is reflection, and the corresponding symmetry element is called plane of symmetry. This is POS, and it is denoted by sigma. Number 3, this is the inversion, and the corresponding symmetry element is called center of symmetry, COS, or inversion point, and it is denoted by I. And the number 4 is rotation plus reflection, and the corresponding symmetry element is called improper axis of symmetry, where the Cn is called the proper axis of symmetry, and it is denoted by Sn. And the fifth one is the identity operator. Fifth one is the identity operation, and every molecule possesses its identity operation, and it is denoted by E. If we do nothing on the molecule, that will give a same molecule, and which is the identity operation. Clear? Now let's discuss all the symmetry elements one by one. First one, the number of symmetry element is symmetry element is axis of symmetry. Axis of symmetry is an imaginary axis passing through a molecule and rotate the molecule by a certain angle. By a certain angle about this axis, we get an equivalent configuration. So let us an example of H2 molecule, where H1 label these two hydrogen as in H1 and H2. If we rotate the molecule about an imaginary axis which is passing through this oxygen atom, this oxygen atom, and rotate the molecule by about 180 degree angle, we get an H2 H1 with these two are equivalent configuration. So the axis of symmetry is an imaginary axis when passing through molecule, and rotating about this axis, we get an equivalent configuration. Clear? Now it is denoted by Cn, where n is the order of rotation, and the value of n is given by 360 degree divided by theta, where theta is the angle of rotation, by which we can get equivalent configuration. Clear? Now for H2 molecule, we get an equivalent configuration by rotating about the bond axis by angle of 180 degree. So here value of n equal to 360 degree divided by 180 degree equal to, so H2 molecule has a C2 axis of symmetry. Clear? Now let's take another example like BF3, boron trifluoride. BF3, which is a planar molecule. It looks like B, F. For clear visualization, let's take. Okay. Now this is the boron atom. This is F1. We label this as a F1, F2, F3. F1, F2, F3. And if we pass a plane, imaginary plane passing through this only boron atom, just and rotate the molecule passing through only boron atom, and rotate the molecule by angle of 120 degree. So we get an equivalent configuration. This F1 by by 120 degree, we get the F1 will be here F2 and F3. This is an equivalent configuration. Clear? So here the value of n equal to 360 degree divided by 120 degree equal to 3. So BF3 has a C3 axis of symmetry. Clear? Now besides this C3 axis of symmetry, if we pass an imaginary axis which is passing through this BF bond axis and rotate the molecule by 180 degree angle, so we also get an equivalent configuration. So if we rotate the molecule by this axis by 180 degree, we also get an equivalent configuration. So BF3 also has a C2 axis of symmetry, as for 180 rotation n equal to 360 degree divided by 180 degree equal to 2. Now for BF3 molecule has one C3 axis of symmetry and 3 C2 axis of symmetry. Clear? Now if a molecule possesses more than one axis of symmetry, then the higher n value is principal axis of symmetry, and the lower n value is called subsidiary axis of symmetry. So for BF3, C3 is a principal axial symmetry and C2 is the subsymmetry axial symmetry. Clear? And also this C3 axial symmetry is perpendicular to the 3C2. Clear? Now for in a simple way, if during rotation the number of atom rotate is the value of n. For example, if this is BF3, if during rotation of 120 degree angle through this boron atom, all the 3 atom changes its position. So here the value of n is 3 and it has a C3 axial symmetry. If we rotate about this Bn bond axis, then only 2 fluorine atom changes its position. So it has a C2 axial symmetry. Clear? This is all about the axis of symmetry. Now coming to the second one, which is plane of symmetry. Denoted by sigma. Now, if a plane pass through a molecule, show that one half of the molecule will be exactly mirror image to the other half, then the molecule possesses a plane of symmetry. For example, if we take water molecule as an example, H1, H2, just like that. If we put a plane passing through this oxygen atom, what we get? Then this half will be the exactly mirror image to this half. Clear? So water molecule, so it has a sigma. Clear? Now this plane of symmetry, that is the plane of symmetry, is a plane which bisects the molecule into 2 equal halves. Clear? Now this plane of symmetry are of 3 types. Number 1, vertical POS, horizontal POS, dihedral POS. And vertical POS denoted by sigma V for vertical, horizontal sigma H for horizontal, and dihedral sigma D for dihedral. Now what is vertical plane of symmetry? When the plane contains principal axis of symmetry, that is the plane is parallel to the principal axis of symmetry, then it is called sigma V. Okay? And what is horizontal plane of symmetry? If the plane is perpendicular to the principal axis of symmetry, it is called sigma H. Okay? Now let's take an example of BF3 molecule. So this is the BF3 molecule. It has a C3 principal axial symmetry, which is passes through this atom. If we put a plane containing this BF bond, and which bisects this molecule into 2 equal halves, that is this part is exactly mirror image to this part, so it has a plane. It has a plane of symmetry which is parallel to the principal axial symmetry. So it has a sigma V. So how many sigma V are present? There are 3 sigma V present. One plane is passing through this BF bond, second one through this BF bond, and third one through this BF bond. Clear? So it has a 3 sigma V. Now this BF3 is a planar molecule, so it has a molecular plane, and this this plane is perpendicular to this principal axis of symmetry. This plane, the molecular plane, perpendicular to the PA, so it has a sigma H. Clear? So this BF3 molecule, has 3 sigma B and 1 sigma H. Clear? Now what is the sigma D, sigma dihedral? Now if a plane passing through principal axis which bisects the angle between two bisect the angle of two subsidiary axis. Clear? Now for example, let alene, the structure of alene looks like here. That two hydrogen, if the two hydrogen of this terminal carbon lies on the plane of this hoverboard, then the another two hydrogen of this carbon, one must be the above the plane, another must be the below the plane. So one is, this is the hydrogen and the other hydrogen lies on the below the plane. Clear? It has a 2 sigma d orbital. It has a 2 sigma d plane of symmetry on this. Okay. One lies on this, and then this. It look not so clear. So this plane of symmetry on 3 carbon atom, on 3 carbon atom plus 2 planar hydrogen, and the second one 3 carbon atom plus 2 out of plane hydrogen atoms. Clear? So it has a C2 Clear? This is toxis. Okay. Now coming back to our next symmetry element, which is the inversion center. If a molecule, in a molecule, a atom is joined from the center of the molecule, and the line is extended to the same extent in the opposite direction, and same atom are, if this atom are present here, then the molecule is supposed to then the molecule contains center of symmetry. Clear? For example, if we take benzene, then from the center, these 2 carbon atom are in opposite direction, and but the distance of this carbon and this carbon are same from the origin. Similarly for this. So benzene molecule has a center of symmetry. Generally, upon operation of the inversion on any Cartesian point having coordinate x, y, z, upon inversion operation we get minus x, minus y, minus z. That's why it is called inversion point. If we take another example of PtCl4 2 minus as an inorganic complex, it is a square planar structure. So Pt, it looks like this. So it also has a center of symmetry. There. Now the third one, now last one is the improper axis of symmetry. Symmetry. It is denoted by Sn. It consists two symmetry operation. One is rotation and the second one is reflection. Okay. Now if this is done by two ways, one is the rotation followed by perpendicular reflection, that is rotation Cn perpendicular to sigma, and second one is reflection followed by perpendicular rotation divided by Cn sigma. Okay, so Sn equal to sigma Cn equal to Cn sigma. For example, if we take methane molecule, which is a tetrahedral structure, like if carbon atom lies at the body center, and hydrogen atom are placed at all the alternate corners. So it is the structure of CH3. Now if we rotate the molecule by 90-degree angle, that it has a C4 axis of symmetry. So what we get? We get this term. If we label this as a H1, H2, H3, H4, this is the carbon. The H1 will be here, H2 will be here, H3 will be here, and H4 will be here. Now if we pass a plane which is perpendicular to this axis, perpendicular to the C4, this is a plane, put a plane here, sigma, then we get carbon H3 will be here, H4, H1 will be here, and H2 will be here. So these two are equivalent configurations. So methane molecule has CH3 has S4, that is C4 plus sigma, C4 sigma has S4 axis of symmetry. That means sigma C4 sigma, or sigma followed by C4. Okay. So this is all about the symmetry elements and symmetry operation. and using this symmetry elements and symmetry operation we can easily calculate the point group of a molecule, and that will be discussed in our next video. Thank you.